In this lesson, we're going to explore the idea of organized counting. So we're going to put probability away for a little bit. We're not looking at the idea of what are the outcomes and how likely are they to happen. Instead, we want to just figure out what are the different combinations of outcomes. And we often do this when we look at compound events, so one event happening after the other. And we're going to use our old idea of a tree diagram. But again, rather than putting probabilities on it, we're just going to make branches list the different kind of outcomes. Okay, each branch signifies a stage to the problem. So stage 1 here has 2 branches. There's 2 different choices. Stage 2 had 3 different choices. And stage 3 had 4 different choices. If I want to figure out the number of choices altogether, I'm going to count the number of leaves. Leaves are things that are at the end of a branch, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 12 more. So there'll be 24 different choices of these different combinations. Now, we don't have any options here. We don't know what the stages are made up of. We can look at some examples where that is given to us. So, at a private school, students wear school uniforms. Each student must wear either a white or blue shirt, and either pants are gray, black, or navy. Using a tree diagram, we want to illustrate the possible clothing combinations. So, stage 1 is we got to put the pants on. Oh, sorry, shirt on. That's how it's worded in the order of the question. Okay, so our shirt could be either white or blue. Now, in the old unit, when we talk about probability, we'd say 50-50, but we don't care because all of these things are 50-50 if there's only 2 choices. So we don't need probabilities anymore, just the list of things that could happen. The next choice is I gotta put some pants on. So what could they wear? They could wear gray pants, black pants, or navy pants. And these are each would be a third if we're talking about probability, but again, I don't really care about that. What I care about are just the lists of things that they could wear. So how many different possible clothing combinations are there? Well, if I look at my leaves, the things at the end, there are 6 possible combinations. And I can make a list of them if I wanted to by following each set of branches through my tree diagram. So one list would be a white shirt, gray pants, white shirt, black pants, white shirt, navy pants, or blue shirt, gray pants, blue shirt, black pants, blue shirt, navy pants. Okay, let's try another one. A test. It has 4 true or false questions. Draw a tree diagram that shows all possible combinations. So what are the stages? We got to answer question number 1, then question number 2, then question number 3, and then question number 4. Well, question 1 could be answered as either true or false. Question 2 could be answered as either true or false. And it doesn't matter what we did the first time, we have both options the second time. These would be those independent events, right? Each branch you start all over again. Third one, we have true or false. And again, it didn't matter what happened previously. These are all true or falses. And then the fourth one, well, we got true or false again. This runs out of room really quickly once you make these big tree diagrams. And the more stages you have, and the more choices each stage you have, the bigger your tree diagram is going to be, the messier it's going to get. How many different possible combinations are there? Well, if we go through and count, we've got 2, 4, 6, 8, 10, 12, 14, 16. There are 16 different possible combinations of answers to this test. Again, we're counting the leaves at the end. Now, tree diagrams aren't hard to make, but as I was saying, the bigger they get, the more stages you have, the messier they're going to get. So we don't really want to have to rely just on tree diagrams. We want to be able to think about things. Kind of like when we did probability, we could do experiments, but theoretical is kind of more handy to us because we don't actually have to do the experiment. So here's our big idea. There's something called the fundamental counting principle. The fundamental counting principle shortens the tree diagram idea. What it does is it says if a task is made up of stages, questions, true or false, and true or false, and true or false, you got to put pants on, you got to put a shirt on. So stages with separate choices. The total number of choices is given by m times n times p. where M is the number of choices in the first stage, N is the number in the second, P is the third, and so on and so on and so on. So if you're thinking the word and, I got to do question 1, and I have to do question 2, and I have to do question 3. Well, then I'm trying to multiply these things. So if we go to the previous one for just a second here, how many choices do we have at stage 1? We had 2, true or false. Stage 2, 2, true or false. Stage 3, true or false. Stage 4, true or false. And if I multiply those all together, I end up with 16. And the same is true with the even one before that. We had 2 choices at the beginning. We had 3 choices for our pants. 2 times 3 makes 6. So totally shortens the tree diagram idea and allows us to do things that are a little bit faster, but still get the number of combinations. The only trick is we have to think about what are the choices and what are the stages. So let's try some examples here. We have an all-star baseball team. They have a roster of 7 pitchers and 3 catchers. How many pairs of pitcher and catcher can the manager select from this roster? So what do we need? We need a catcher and we need a pitcher. And we have 2 stages. How many choices do we have at each stage? Well, we need 3 catchers to choose from and 7 pitchers. And I notice I said the word and. Well, and means multiply. So we have 21 different combinations. If you really wanted to, you can make a tree diagram. You'd have to have 1, 2, 3, 4, 5, 6, 7, and then off each of those all your catchers, right? If you add that all up, you're going to get the same answer, but this is way messier to have to deal with than just 7 times 3. Okay, but if you need help starting a problem, a tree diagram will always be our go-to tool when we have stages. Let's try the next one. 4 dice, different color, are rolled. We always said different color for dice. We then examine the uppermost face of the dice. So we roll the dice, and we look at this combination and say, okay, I got a 2, a 5, a 2, and a 6. I want to know how many different configurations are possible. So I roll that. That's a different configuration now because the first number used to be a 2, now it's a 1. So every time I roll the dice, odds are I'm going to get a different configuration, right? How many can we get? So what are the stages to this problem? Well, I got to roll the first dice. How many different ways can I do that? Well, I stop and think about it. It could be a 1, a 2, a 3, a 4, a 5, or a 6. There's 6 combinations. And I got to roll the blue dice. Again, there's 6 combinations. So off of this, there would be 6 more. So I've got 6 here. And the next one's also 6. And the next one's also 6. So these tree diagrams starting to get pretty messy here. 1, 2, 3, 6. And off of that, 1, 2, 3, 4, 5, 6. So do I really want to make that? I've only done one sort of branch of the tree diagram, but the math is way easier by just doing the calculation. So 6 times 6 times 6 times 6 gives us 1296. Okay, isn't that much faster than trying to draw a tree diagram and count your paths? Right, we're going to try a couple more. A teacher makes up a multiple choice test. Each question has either A, B, C, or D as the correct answer. On a 10-question test, you're going to randomly guess. Well, how many different solutions are possible? Now, I don't mean how many right answers are. There's only one right answer, right? But how many different ways could you guess on this test? Well, it's stages. We got to guess on question 1. How many different choices do we have? 4. And 2. How many choices? 4. And 3, and so on, and so on, and so on. We're going to do this 10 times. So we could write this out as 4 times 4 times 4, 10 times. That would not be wrong. That's kind of messy to write this. We actually know a faster way of writing this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Need one more. It's way faster to say, oh, there's 4 choices 10 times. And if we do that, it turns out that there's 1,048,576 different combinations of guesses you could make. You don't want to go through all those for sure. Let's try another one. Okay, these take practice. Every question is different. Yes, there are similarities in terms of, hey, it's stages and choices. We actually have to read each question and think about each one independently. Let's try the next one. Maybe pause it. Try it yourself, see if you can figure out the answer, and then check. So we have a license plate. It consists of 3 letters followed by 3 digits. And we want to know the different number of license plates that could be made. So I need to have a letter, a letter, a letter, and then I need to have a number, a number, a number. So how many ways could I do the first thing? How many different letters are there? Well, there's 26 of them. And the next letter, okay, there's 26 of those. And the next one, 26 of those. And then I need some numbers. Now careful here. Most people think the numbers 1 to 9, but don't forget about the number 0. There's actually 10 choices for numbers. So 10 and 10 and 10. Or if you want to, 26 to the 3 times 10 to the 3. That's the exact same answer, right? Okay, put that in our calculators. We got 17,576,000 different combinations. Okay, that's part A. Part B, would the answer change if the letters and digits were alternated? So in other words, if I went letter and then number and then letter and then number, would that change my mathematical answer? Well, no, it wouldn't, because I still have 26 times 10 times 26 times 10 times 26 times 10. When you're multiplying things together, the order you multiply in doesn't change the answer in the end. 2 times 3 is the same as 3 times 2. Right? How about part C, however? Is that a different question? How many license plates are possible if every spot could be a letter or digit? So, I could have a letter or a digit for all 6 of these spots. Well, that's going to change things. Because if the first thing could be a letter or a digit, well, now there's 36 choices, the 26 numbers and the 26 letters and the 10 numbers. And same thing for the next one, and same thing for the next one. So I've got 36 to the power of 6. Well, that's a different number. That's a much bigger number. That's 2,176,782,336. Much bigger number. Okay. So when provinces run on license plates, they don't necessarily change the order of things, but they may change what's allowed in each spot. And that can totally change how many license plates you make. Okay, let's try the next one. Okay, a couple more of these. A large room has a bank of 8 light switches. Each light switch can be on or off. How many different arrangements of switches are there? So what are the stages of this problem? When I go to the first light switch, it could be either on or off. The next one could be on or off. In other words, there's 2 choices at each stage. How many stages are there? 2 times 2 times 2 times 2? 8 times. So we have 256 choices. Yeah, that's an easier one. But we have to be able to think about our stages and our choices. Okay, I got a couple more for you. A playlist contains 5 songs. If they're played randomly without repetition, how many different orders of songs could you hear? Now this question is slightly different than the previous ones. There's one big idea here. This without repetition. Why does that matter? Well, when I play the first song, I've got 1, 2, 3, 4, 5 choices. But once I've played a song, let's say I played that one, I can't play it again. So when I go to the next stage, I don't have 5 choices anymore because one of these songs is gone. I've only got 4 choices now. And we're doing and, right? First song and second song. And then once I play that song, I can't use it again. So now I got 3 choices, and then I got 2 choices, and then I got 1 choice. Okay, so we have to be careful that we're reading words carefully, because sometimes you're going to be given information, kind of really important information, that totally changes the question. If we were allowed repetition, we'd have 5 to the power of 5, 5 choices 5 times. But no repetition, my values actually change as they go. Okay, last one. Using the digits 3, 4, 5, 6, 7, 8, 9, how many 4-digit numbers are possible without repetition? No repetition allowed. Well, I've got 1, 2, 3, 4, 5, 6, 7 numbers. So I'd have 7 choices for the first number. I can't repeat. So I only have 6 choices for the next one, then 5, and then 4. And remember, it's only a 4-digit number, So I'm not going to go all the way down to 1 this time. I'm just going to have that, and that comes up to 840. But if repetition is allowed, like part B, I've got 7 choices for the first number, and I can have 7 choices for the next number, and so on and so on. So I've got 7 to the 4, or 2401. Okay, lots of thinking going on here. Okay, for the rest of the questions, we're going to assume no repetitions allowed. We're still making 4-digit numbers. Part C, we can only use odd digits. So I can't use the number 4 because not an odd digit, but I could use a 3, a 5, a 7, or a 9. How many different combinations are possible? Well, I've got 4 ways of picking the first number, the 3, the 5, the 7, and the 9. But once I use the number up, I can't repeat. Well, now I've only got 3 choices for the next, and then 2 for the next, and then 1 for the last, and I have 24 different combinations. If the 4-digit number is an odd number, what does it mean to be an odd number? It means that at the end, you have an odd digit. Okay, so I need to think about this in terms of how do I make this an odd digit? Well, I can do that if I pick one of my odd digits. And how many odd digits do we have? We've got a 3, a 5, a 7, or a 9. So there's 4 choices of ways I can fill this spot. Okay. Once I put a number in that spot, I can't use it again. So there's 6 digits left over. And these other 3 spots can be filled with those 6 digits. But remember, no repetition. So I've got 6 choices for this one, and then 5 choices for this one, and then 4 choices for this one. And I've got my 4 choices for my odd digit. And if we do that, we end up with 480. And that's a bit of a trickier one. How about things that start with the number 4? So in other words, I put the number 4 right here. Well, if I put the 4 there, it's gone. I've used it up. What am I left with? I'm left with all the other digits. How many of them are there? Well, there's 6 choices for this number. No repetition, so 5 choices for this number and 4 choices for this number. And I get 120. Now notice this time the number 4 isn't a choice, it's the number 4, right? The choices are actually the other 3 spots. Okay, how about we try F? Things that are starting with a 4 and are odd numbers. So the number 4 has to go here. It's gone. We used it up. But I also need to have it being odd. Well, odd, I've got the numbers 3, 5, 7, and 9. So I've got 4 choices. Okay, I've used up 2 digits right off the bat, the number 4 and one of the odd numbers. So I'm left with 5 things for this spot and 4 things for this spot. So 5 times 4 times 4 gives us 80. And then the last one, things that contain a 4. So I need a 4-digit number that contains a 4. So here's a tricky one again. It could start with a 4. But that's not the only choice. It could be a 4 right here. Or it could be a 4 right here. Or it could be a 4 right here. So now we're beyond tree diagrams. We're thinking about cases. When we think about cases, we have to think about the word or. And the word or means we're going to have to add up the different number of choices, like we did with our tree diagram back when we did probability, and we had to go through the branches and add up the separate branches. So let's look at each of these cases separately. If I put a 4 in first, it's gone, it's used up. I've only got 6 digits left for the next spot, and then 5 digits, and then 4 digits. 6 times 5 times 4 is 120. If I put the number 4 in the second spot, it doesn't really change the question. There's still 6 choices, and then 5 choices, and then 4 choices. I'm just skipping over this spot because it's been filled in. Again, I got 120. And the same for the third, and the same for the fourth. Okay. Altogether, this is going to give us 480 different choices. Okay, there's our introduction to counting. Some basics. Now, I know that doesn't seem very basic, but it really is the basics of counting. So we're going to try some questions. You need to try this stuff in this section of the course. Every question is different, and some of them are pretty challenging. You have to really stop and think about what's going on here. If you need to draw a tree diagram, do. That's a good starting point, but unless it says so in the question, you don't have to.